Okay, we've got another projectiles question here. An arrow shot from, well, let's say the origin, but it lands on a target 10-5, so it's actually fallen 5 meters below where it was shot from. They've given us the initial velocity and the angle, and we've been asked to prove certain things about its trajectory and possible values of theta. So let's have a go at it. Okay, I've drawn the setup. So what we need to do is we need to find motion equations for both the horizontal and the vertical, and then try to show there is a relationship, this relationship of tan to the -1 squared is equal to 1. If we treat the vertical and horizontal motions separately, the one thing that will be common is that they will find their target at the same time. So we can remove time from the two equations that we get, and I'm sure that's where we'll find that this relationship that they've said here in part A to be true. So let's make a start. In both horizontal and vertical planes, we've been given a displacement. So the best equation to solve this will be S is equal to ut plus half at squared. And also, before we start, we need to resolve the velocity, which set off at an angle theta, into both horizontal and vertical components. So we need to turn this 10 meters per second through an angle of theta. In doing so, its value will be multiplied by the cosine of theta, thus reducing its oomph, if you like. So horizontally, we get 10 cos theta as a horizontal velocity. We will have to turn 10 meters per second through this angle here, which is 90 minus theta. So vertically, this will give us 10 cos 90 minus theta. Because of that trigonometric relationship that the cosine of 90 minus theta actually equals sine theta, so I can write this more conventionally and probably more neatly as 10 sine theta. Okay, let's apply solve that equation horizontally first, with going to the right as positive. We have a positive displacement of 10 is equal to the u, which is 10 cos theta, and this will be multiplied by the time, which we don't know. And because there's no acceleration horizontally, we can ignore a half at squared. So simplifying our horizontal motion, we can get rid of the 10. Given that I'm going to be solving for t, my best version of this equation is that t will be equal to 1 over cos theta. So vertically, and let's choose going up as positive. Yes, we're going to have to apply the whole of this equation because we have the acceleration due to gravity, which will be taken as 10 meters per second squared. Now, vertically, the displacement goes all the way up in the air in a positive displacement, falls down and goes past zero and eventually ends up as a negative displacement. So our S in this case is -5 is equal to the initial speed, which is 10 sine theta, and that's multiplied by t plus a half. The acceleration, as we've said, is -10 t squared. Half at squared. Okay, simplifying, I get -5 is equal to 10 t sine theta minus 5 t squared. Now I can take a common 5 out of all of this equation, so I get -1 is equal to 2t sine theta minus t squared. So if I call this equation 1 and this equation 2, I can substitute equation 1 into equation 2 and get rid of t. Because notice that t is not in our equation that we've been asked to prove. So sub 1 into 2, and we get -1 is equal to 2 sine theta over cos theta minus this guy squared. So this is 1 over cos squared theta. Now you should be thinking about your Pythagorean trig identities here. The good thing is that we've got 2 tan theta here already, because if you look at the multiplication out of tan theta minus 1, we get tan squared theta plus 1 minus 2 tan theta. So here we are, this guy is 2 tan theta. So this term is part of the answer. What have we got to do to this to transfer it into tan? Well, 1 over cos squared is sec squared theta. And if you remember, one of those Pythagorean trig identities is that sec squared theta equals 1 plus tan squared theta. We're nearly there. Okay, so this becomes negative 1 is equal to 2 tan theta. This, remember, is sec squared, but I have to multiply both these terms by negative 1, so we get negative 1 minus tan squared theta. All we've got to do is rearrange the furniture here. Let's actually multiply through by negative 1. So I get 1 is equal to negative 2 tan theta plus 1 plus tan squared theta. Again, rearranging the furniture and swapping sides, I get tan squared theta minus 2 tan theta plus 1 is equal to 1. Well, as I hinted already, if you multiply this bracket out, you will get this. So this indeed factorizes to tan theta minus 1 squared is equal to 1. And that's what we were asked to prove. So with not much room left, let's have a look at part B. We're asked to find the possible values of theta. Well, this is just solving this equation. So if I take square roots of both sides of this guy, I will get that tan theta minus 1 is equal to plus or minus 1. So therefore, tan theta is equal to 1 plus or minus 1. So our 2 possible values of tan theta are that tan theta is equal to 1 plus 1, which is 2, or tan theta equals 0. So our 2 answers for theta will be that theta is equal to tan to the minus 1 of 2, or tan to the minus 1 of 0. So if you look these up on a calculator, we get that theta is equal to 63.43 degrees, or that theta is equal to 0. So yes, so it proves that we can shoot the arrow right along the ground and it will fall exactly in the same way and hit the target. Or you can shoot it up in the air at 63 degrees and it will also follow the red line trajectory and hit the target at 10, -5. So those are the 2 answers they require. We're done.